So, welcome back. So, we shall be continuing our discussion on the homogeneous test strategy. So, we have been discussing about the relationship of NICVK with TVLA, and this was where we stopped in the last class. So, we basically now have a pretty much relationship how to calculate the NICV or we know how to calculate from TVLA the NICVK, and essentially we know how to calculate we have basically related TVLA with NICV2 and we have related NICV2 with NICVK. Okay. So, now we will see how we can relate the NICV to the success rate or the SNR to start with. Okay. So, we have got NICV which is equal to 1 divided by 1 plus SNR. Okay. So, you remember that this is something that I already defined in the previous class. Okay. So, NICV you can actually write as 1 divided by 1 plus 1 divided by 1 plus 1 by SNR. Okay. And therefore, you can essentially write the SNR as 1 divided by NICV k minus 1. Okay. Note in this case NICV in the general setting can be written as NICV k. So, now we have got the SNR, we basically can link till the SNR, but how can we get the success rate? So, the relationship between the SNR and the SR was established in the work on confusion coefficient matrices and vectors, and I will quickly try to give an overview behind this result. Okay. So, therefore, let us define suppose you have got KC which is your secret key, and suppose I tell that KGI, that means anything apart from the secret key is defined as KGI, where I varies from 1 to 2 to the power of n minus 1, which is the key guess which is due for KC. Okay. So, now if you do it, then we define certain vectors and matrices. So, these vectors, there are 3 vectors. The first one is called as coefficient vector k or kappa, and the confusion matrices are k and k star star. Okay. So, how they are defined are as follows. So, you have got this is your kappa, which is your corresponding as you can see that there are from 1 to 2 to the power of n minus 1, that means for all the wrong key parts, remember that you are guessing only a part of the key, okay, and not the entire key. So, therefore, this exhausting analysis is possible. Okay. So, therefore, you basically have got in kappa there are 255, for example, if it stands for 256, suppose you are doing it for AES, then this will have 255 values. So, you are basically doing this calculation of kappa with all with KC with KG1, KC with KG2 and so on. Okay. Then you calculate the matrix K and the matrix K star, again using some other definition of kappa where there are 3 parameters. So, in one parameter there are in one definition of kappa there are 2 parameters, and in another one there are 2 parameters, there are 3 parameters. Okay. So, again you note that how the matrix has been defined. So, you have got KC as the first argument in all of them. The second argument is varying pretty much depending upon the row and the column positions. Okay. So, you have got KG1, 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 KG2, so until KG1, KG2 to the power of n minus 1, and in the if you see the last row it is KG2 to the power of n minus 1, KG1 and so on. Okay. For K star star you have got another definition of kappa which is kappa star star, for example. So, how do you define? I am not going into the derivations behind them, but just writing down the results here. So, you can see that the kappa of Kc comma Kg is defined as the expectation of L x comma Kc minus L x comma Kg. Remember that L was my leakage function. So, therefore, I am using L to estimate the leakage. Okay. So, this is your input and this is the corresponding key. This is the correct key and this is the guess of the key. Again you can calculate kappa Kc comma Kg Kgi comma Kgj. So, there should be a Kgi here, Kgi comma Kgj, by using this expectation, which is again like something like you have got the leakage of x comma Kc minus leakage of x comma Kgi. This is one part. You multiply it by L of x comma Kc minus L of x comma Kgj, and then you find out the expectation of this parameter. Again, when you have got 3 terms, then you have got something like 4 times expectation of this whole square, again multiplied by L of x comma Kc minus L of x comma Kgi multiplied with L of x comma Kc minus L of x comma Kgj. Okay. So, at this point let us not let us just try to kind of take these definitions and rather try to apply this in our context. Okay. So, the idea is that here for all these parameters you can see that there is a term called Kc which stands for the actual key. Okay. But in order to apply this, the good thing is that you need not know the key. If there are no weak keys, then these parameters are not key dependent. So, therefore, pretty much you can work without loss of generality with any key, and you can actually set Kc equal to 0 and do your calculation without even knowing what is the actual key. Okay. So, now there is a formula which you can directly apply. So, if you remember, the success rate was defined by this probability, right, the probability of an adversary that if it is operating on K0 and observing the leakage L, it predicts the value of key as correctly as K0, okay, then we say that the attack is successful. So success rate is nothing but the probability of this success, okay. So if we assume that the leakage is, as we have assumed, y equal to epsilon L plus n, then this theoretical SR can be found out by this cumulative distribution function, okay. So it is phi, and you can observe that there are two parameters here, like there is a phi c and there is a mu, okay. So this essentially stands for the cumulative distribution function of the multivariate normal distribution. We have seen already a multivariate normal distribution in one of our previous classes, where the mean vector is mu and the covariance matrix is C, okay. So the covariance matrix C is defined by this formula, which is k plus epsilon by 2 sigma whole square into kappa into k star star minus kappa transpose, okay. So you can see that if you know k star star and if you know kappa, then you can estimate this covariance matrix, okay. And all these things, right, are defined over here. So these three things are defined over here. Using them, you can know this covariance matrix, okay. What about this part? So this is your mean, okay. So this is parameterized by root q into epsilon by 2 sigma into kappa, okay. So this, remember that, you know, like if you remember the expression for SNR, okay, so then what you can do is you can easily manipulate this part and you can write it as root q into half into square root of SNR into kappa, okay. So why SNR? Why SNR? Because you remember, right, this is the square root of SNR, okay. So the SNR is nothing but epsilon square by sigma square. So therefore epsilon by sigma you can write as square root of SNR. So therefore now if you know the SNR, from there you can estimate the success rate by finding out this cumulative distribution function and by finding out the value of this parameter, okay. By finding out the value of this parameter and finding out the, you know, like the essentially estimating this this probability function, or rather this cumulative distribution function, okay. So therefore what we have seen here now is that we have been able to go to the SNR, and once you are able to estimate the SNR, from there you can know what is the corresponding success rate, okay. So with this background, we are all set to propose our test methodology. So what we will do now is we'll go from I equal to 0 to k, okay, and we will do this partitioning. We'll partition the side channels into traces into two groups, G1 and G2. In G1, we have got side channel traces where the jth byte of the intermediate data takes a value I, and in the G2 it does not take the value of I, okay. So then we apply the TVLA on these groups G1 and G2, okay. Note that this is an example of a specific TVLA test, okay, because we are specifying the corresponding intermediate data. And once you have got TVLA, from there you can quickly derive what is NICV2I by using our formula. Once you have got NICV2I, remember that, and you have done that for all these k groups, you can sigma them, and from there you can estimate the value of NICVK. Once you have got NICVK, you can estimate the SNR, and then you can fix this SNR, and from here you can get the success rate, okay. So note that in this particular approach, the leakage or the actual leakage model is only required at this step, in the 9th step, okay, whereas the previous ones you can do agnostic of that, okay. And that is good because you can, you know, like try various leakage models, and you can do your attack with various assumptions, okay. So therefore this is my proposed test methodology. So what we do is basically initially we do a non-specific TVLA, we do a pass-fail test. If it passes, then we say that it is fine, whereas if it fails, then we still do a further analysis, because as we know that, you know, like if there is a failed TVLA, it may still mean that the attack will not work, and in certain application scenarios like automotives, or where, you know, like where you essentially, right, you can afford, you know, like low cost countermeasures, or often where you will be employing low cost countermeasures. So there we you know, like if I want to do an analysis, then probably you have to again apply your evaluation test methodology, and you have to do the attack again and again. So that would be costly. Rather, you can replace that part and do this approach where you, if it fails, you compute a specific TVLA, and then you compute the SNR, and then you compute the attack potential or the success rate, okay. So here note that if you want to predict this, you need this leakage model. So the leakage model is only required at this step, okay. And then again you answered whether the attack potential is acceptable within the acceptable limits. If it is fine, then you say it is secured. If it is not, then you again then you can say that the design is vulnerable with so many amount of traces, okay. If you remember that in the previous case, right, in order to do this attack, if you remember, right, there was a loop in the graph, okay. So because we are doing the attack again and again, okay, but here that loop is gone, so you need not do it again and again. So this methodology is quite fast in that sense, okay. More or less, right, observe that the choice of intermediate variables is only required at 2 steps when you are computing the specific TVLA and where you are computing the attack potential SR, okay. So this part you can actually parallelize by trying various target variables at the same time. So you can kind of parallelize this process and you can even speed up your test methodology. So therefore, right, if I compare with evaluation and conformance, then these are essentially some of the observations. You can see that yes, it requires a leakage model, the intermediate value is also required, the vulnerability quantification is also done, and it is also a very analytical approach, okay. So therefore, it is pretty much kind of like doing or rather nicely kind of combining both the approaches, and is also not only doing a yes no analysis like your TVLA, but is also able to give you an actual quantification on the success rate, the number of traces which you need to do the attack. So therefore, it is, I would say, a more detailed analysis, okay. So let us now quickly look about if I have this approach and if I want to apply it on certain experiments. So the experiment has been done on a Sakura GW platform where we have an Atmega 8515 smart card, okay, and we basically again use our power attack setup where we have an oscilloscope which is a mixed signal oscilloscope, and then we basically target an AES implementation, which of course is an unprotected implementation, and therefore this should break or should be vulnerable if I do a TVLA analysis. That means I should get a TVLA value which is probably more than say a given threshold of 4.5, for example. So we will analyze our protocol, our proposed test methodology for 2 different variants of AES. Actually, in one case I will be simulating the AES traces for an 8-bit microcontroller. In the other case, we will be doing the test on an actual Atmega smart card, okay. So in the first case, you can observe that this is an example on the simulated power traces. Again, we have basically simulated the traces for an 8-bit microcontroller assuming a perfect Hamming weight leakage, and then we have added a 0 mean Gaussian noise to it. So the idea is that the side channel traces are now generated by using this HW, that is the Hamming weight of V plus the noise, and this V is again like the chosen intermediate value, which in this case is the first 8 bits of round 9 output, okay. And then we add a noise, so we add noise and we kind of vary the SNR from something like 0.03 to 2. You can observe that so we not only do, we basically do an estimation of the success rate or the traces required for a success rate of 80%. So note that what I can do is I can go back to this equation and I can pretty much fix the success rate and from there try to estimate Q, which is the number of observations, okay. So therefore, what I do over here is I basically estimate the number of traces required for a success rate of 80%. That means I fix the success rate, and then for a given SNR I basically plot our expected, that is the theoretical graph or theoretical profile, as well as we also do a real life power attack and try to match the results, okay. You can observe that the match is quite close, and in fact, right, if you observe very minutely, you will find that when the SNR is high, then the deviation is little more, okay. So why? Now because when the SNR is high, then the attack is actually happening with very less traces, okay, and therefore, right, statistically you have got less samples, and therefore, right, there is a small overshoot which you can observe in this case, okay. But otherwise, right, there is a very close match, and essentially our theory pretty much follows what is essentially happening experimentally. So it can be observed that under perfect Hamming weight model assumption, the estimated theoretical estimation and the practical computations fits quite closely. A minor overshoot for practical SR is seen for high SNR points, typically more than 0.5, and the overshoot is an approximation glitch in the theoretical formulation, because as we know that we have been applying central limit theory and the law of large numbers does not work when you have got few traces to observe, it does not really converge. And otherwise, right, the approximation overshoot remains constant even for extremely high SNR. You are tested up to SNR equal to 20 and the match is quite consistent. So let us try to look into a real trace. So in this case, interestingly, you see that this is an Atmega experiment which has been performed. There have been several traces which has been taken from, say, large number of traces, and you have basically randomly chosen say a set of 300 traces and done this analysis. So we have basically highlighted here 2 points P1 and P2 in order to show that there are 2 different points in the power trace graph, okay. And then we do this analysis, okay. So we basically add, so these traces are typically taken in a Sakura GW platform where the SNR is quite high, okay. But in order to do our experiments, we added noise to it and try to reduce the SNR and try to see how it compares in that case. You will see that when the SNR is high, then the match is quite consistent, okay. Like this particular trace over here is with for SNR equal to 0.73, whereas here you see that when the SNR is something like 0.16, right, there is a deviation which you can observe. Similarly, right, in this case when I am observing the point P2, right, again you can observe that the match is high, and but still, right, when the SNR is low, the match is not so high as probably this one, but still there is a mismatch, okay. So this gap between the theoretical SR and the practical SR, we can study it further. It is probably because of the improper leakage model. Remember that we assumed the leakage model at the end. So there we assumed in this case a Hamming weight leakage model. So somebody, right, can come up and give us a better leakage model, and if that be so, right, then we can improve the accuracy of our estimate, okay. So how can we improve the leakage model? There are several works, like here in one of the papers in CHEST 2015, there was a work which tells you how to improve by something which is called as a stochastic modeling of the leakage, okay. So in stochastic modeling of the leakage, right, you assume that every bit has a different contribution. So you have got, say, beta I into Vi. So in the Hamming weight model, all the beta I values will be roughly the same, okay. So this is essentially the point P1 and point P2. You can see that the contribution in point P2 for all the points are roughly the same. There are of course some aberrations, but here the aberrations are even more, okay. And therefore, right, the deviation also is more in case of point P1, okay, and that is exactly what you see here, that the deviation is higher compared to this one when the SNR is essentially low. So now what we did is we basically did better, estimated the leakage model, and then we again redid the experiment, and now you can see that if you compare again both point P1 and P2, you find that there is a drastic improvement, and you can see that the match is more close, okay. So therefore, from the methodology aspect, it shows that the better profiled the model is, more realistic prediction can be done on for the success rate from your TVLA results. Nevertheless, of course, the evaluator can test several leakage models in parallel, and and essentially can accelerate the process, without reducing any effect on the accuracy of your test, because you can do pretty much evaluations of this leakage model in parallel, and you can feed and see that which one matches close, okay. And or maybe you can make, I would say, like a worst case estimate depending upon the various guesses on the leakage models, okay. So once you have basically this framework, right, I mean essentially we can discuss about some of the final conclusions based on our observations. So in particular, right, you see that let me just conclude this quickly. So let me just conclude by these comments that CC and FIPS are two popular side channel test strategies. The former, which is an evaluation style, is very costly and requires high skill, whereas the latter, which is a conformance style, is efficient, but it doesn't provide any quantification of leakage or success rate, okay. What we have seen just now is that how we can combine both of them, and we can get a confirmation style combined with your evaluation style, and although you start with the TVLA, you can come up with or estimating some of the metrics of an evaluation style testing methodology, of course with some inputs on the corresponding leakage model, okay. Of course you need the leakage model. Without the leakage model, we cannot estimate the success rate of a side channel attack. So here are some two important references of the discussion. The first one is actually where the original TVLA test was proposed, written by Goodwill and their collaborators, and in the second paper you can find out the entire the more elaborations on the proofs and derivations that we have discussed in this particular talk, okay. So with this I would like to say thank you. Thanks for your attention.